Okay, and so in one of those prior examples, I talked about the turning points on the graph. Well, those turning points are called local minimum or maximums. So see on this graph here, there's a turning point where the graph is changing directions from either increasing to decreasing or vice versa. And see how that happens there? It happens right up here. It happens again right down here, right? Oops, right in there. And then right up here. So this actually changes directions those 4 times. Oops, I'm not get that highlight. And so each of those places represents either a local maximum or a local minimum. Now why we call it local is because, for instance, this point right here, that is not actually an absolute maximum because there are certainly y values that are higher than that because they continue on to infinity to the left of the y-axis, you know, forever. So, but it's local, so it's the maximum value in that location, in that area. So it's called a local maximum. So we would define a turning point to be where the graph changes from increasing to decreasing, or vice versa. Could be from decreasing to increasing. A local maximum or minimum is a point on the graph where there's a turning point. And if the graph is turning from decreasing onto increasing, then that will create a minimum point as it's turning from its decreasing to increasing position. So on the graph, I've marked here in purple local minimums. So local minimums are right here on the graph and right here. And of course you can see they are turning points. And then the local maximums also are turning points on the graph, and they are here and here. I'm going to show you a little video on how to use the graphing calculator to, if you had a graph of a polynomial function, how you could use the calculator to determine what these local minimum and maximum points are. Okay, so we're going to take a look at how to find maxima and minima with the calculator. And the first thing we need to do is we're going to take a look at example A, and we're going to type in that equation into the y equals menu. So that equation is 2x to the third power minus 18x and then plus 1. And so we kind of have an idea of what this is probably going to look like. We've been studying these cubic graphs. So we hit the graph key and kind of see what that looks like on the large screen. And this is kind of just looks like a bunch of, almost look like vertical lines. Well, when you see something like this, what it means is you probably are going to need to adjust your window some. It looks like that the graph goes up higher than what we can see in a standard 10 by 10 and lower than we can see. And so what we're going to want to do is we want to go to the window. So we hit the window key. And let's change it so that we can get it to go up a little higher. It also looks like it doesn't go too far to the left or to the right. So we could change maybe the x-min to -5 and the x-max to maybe just 5. Keep it scaled by 1s. But maybe for the minimum for the y, maybe we want to go down to -25. We'll see how that's looking. Okay, and then maybe go up to +25 on the y max. We'll just kind of see if we need to adjust from there. Okay, and so press enter, and if we hit graph again, let's see what that looks like. And that looks much better. Now we can actually see these places that would represent the local maximum and the local minimum. And so here's how we could actually use the calculator to find those max and min points. So if we hit the second key and the trace key, it's going to take us to this menu where you can see, if you go down to 3, there's minimum. So if we select that, press enter, and we go back to the screen, you'll see that the cursor is blinking. And the minimum is going to be the one that's here to the left of the y-axis. So if we were to just scroll on the graph here, you can see the cursor's moving. And it's asking us a question at the bottom of the screen. It's asking us to determine a left-hand boundary. So what that means is we want to make sure our cursor is on the left-hand side of where we see this minimum value being, and this change in direction. And so we just go somewhere on the left. It doesn't really matter where, just as long as you're on the left-hand side. And we press Enter to establish a lower bound. And you'll see that little arrow that's pointing to the right that came up. So it's saying we're going to start looking for this minimum value here. And now it's asking for a right bound. So now we got to continue scrolling on it. We're going to scroll so that we go past that minimum and stop anywhere to when we get to the right. Here's fine. Press Enter. And notice another arrow goes up, and they're pointing towards each other. And what that means is it's saying I'm going to start here at this left arrow, and I'm going to travel along the graph to this right arrow, facing arrow. And actually it's facing to the left, but the one on the right-hand side. And we're going to look for the very lowest output value, the lowest y value that we can find in that interval. So it's asking, do you want to guess? And I guess you could, if you wanted to, kind of scroll down to where you were thinking, where you thought, the minimum was. This looks like it's maybe the minimum right there. And so we might want to use that as a guess. So we press Enter, but then it's actually going to take us to exactly where the minimum is, or as close as it can get. And so you can see this minimum value occurs when x has a value of 1.7320497 approximately, but the y value is actually the minimum value. So that's negative 19.78461. Now that's, in this area, the lowest that this graph ever goes. You can see, if you look back to the left of the y-axis, this graph is actually going to go lower because there's a part of the graph that goes down towards negative infinity forever. But this is what's called a local minimum. So it would be negative 19.78461 approximately would be the minimum value. Now what about the maximum? Well, now we can go back to second, and we can hit the trace key again. And this time, if we want to calculate a maximum, we go down to 4, or we can just type in the number 4, press Enter, and now you can see the cursor again blinking. So what you want to do, it wants us to establish, well, let's see. Let's get on the other side and let's try this again. Okay. So we have second and trace, and we're going to choose 4 and Enter, and it's going to ask for a left-hand bound. So it actually took that as my left-hand bound. So there we go. And then I'm going to scroll on the graph and watch the cursor go up and over that point where we think it looks like it's the maximum value, over the hill there, and press Enter to establish a right-hand bound. And of course you see the arrows going up there on the graph again. And it's asking, do you want to guess? So you can if you want to, or you can just keep pressing Enter. But you could go to where you think it looks like the maximum point and say, I'm going to guess this is it. Press Enter. And it will tell you what the closest they can get to approximate the maximum. And again, it would be the y value that really represents the maximum value here, and that's 21.78461. But it occurs when the x value is negative 1.73205 approximately. But again, when we're looking for the minimum or the maximum values, and in this case they're actually called local minimum or maximum because they're the ones that are in this particular area that we established with our boundaries, the local maximum would be about 21.78461. So go ahead and give example B a try, and you can tune back in after you give that one a shot, see if you can calculate the maximum and minimum values, and check your work. Okay, so I hope you've mastered the calculator to find the maximum and minimum values. And so here is the maximum value for that function x cubed minus 2x minus 3. It's approximately negative 1.911338. And the minimum, or the local minimum, is negative 4.088662. Okay, so finally we're going to look at an application. And this one is related to art. So an artist plans to construct an open box from a 15-inch by 20-inch sheet of metal by cutting squares from the corners and folding up the sides. Find the maximum volume of the box and the corresponding dimensions. Okay, so we've got this rectangle that is 20 inches on one side and 15 inches on one side. And we want to know what the volume is that this box will hold when it's completed, and what this volume or what this box is going to look like. It's going to be sort of like, say, a shirt box without a top on it. And how this shirt box is created is by taking this rectangle and cutting out corners on every corner of the rectangle, and then sort of folding along where these dotted lines would be, and you can kind of just see them, you know, if you kind of fold up the sides on either way, then you kind of tape those edges together and you've created this little box. Well, we don't know what size of these little squares they're going to cut out, so we're going to just say this is an unknown length, so we'll call it x, so which means this dimension is x right here and this dimension is x right here. So we're going to just like cut this little piece right out. And we're also going to cut this little piece right out on the same dimensions on this side. Same down here and down here. So when we think about the volume, we know that the volume is the length times the width times the height. And so if we thought about the length of this thing, so if we were to fold this back together, then the length actually of this box is not going to be 20 inches, it's going to be 20 inches minus, so this part right here would actually be 20 inches minus an x on either end, so minus 2x. Now the width, instead of being 15 along this side, it's actually this length now. And that's because we took 15 and subtracted an x off either end. So that's 15 minus 2x. And then finally the height. Well, the height is actually going to be this dimension right here. See this dimension right there? When you fold that up, that's going to create the height of the box. And so the height is x. So the volume turns out to be, when I expand out these two binomials and multiply the x through, will be, let's see, 20 times 15 is 300, so that's the first two. Outside 2 would be minus 40x. Inside 2 would be minus 30x. The last two would be plus 4x squared, and all of this is going to get multiplied by x when we're done. So I'm going to group my like terms together. So I've got, and put it in descending order of power. So I really have x that I'm going to multiply by 4x squared minus 70x plus 300. So if I distributed that x through, basically would just raise the power on the x on the variable on each one of these and add an exponent on the end. So it would be 4x cubed minus 70x squared plus 300x. Let me just rewrite this up here again. And so this is our volume function, and all we would have to do was graphing calculator, and then we'll go and put it in the calculator, and we'll look for the maximum. We'll look for the relative maximum, and that'll give us the that value of x that would create the largest volume we could possibly get out of this box. So again, just kind of go through that process that we just looked at on how to calculate the maximum value. Put this in as your function and calculate the max. So I went ahead and graphed that, and I might adjust the window quite a bit because the maximum value was very high up on the graph. And so I ended up changing the window range to the Y maximum to be up to 400. But then I could see the maximum value, that change in direction, and using the stat calculate and maximum function, I was able to identify the local maximum to be x is 2.83 and y is 379.04, and that would be cubic inches. So in other words, when x, that little cutout piece, is about 2.83 inches, then the volume will be its maximum amount, which will be 378.04 cubic inches of space inside that box. So that does it for today's lesson. I will see you in class.